The universe is approximately 93 billion light-years across, in every direction you can point. It has been expanding for nearly 13.8 billion years. In that time, it has produced an estimated 2 trillion galaxies. Each of those galaxies contains, on average, somewhere between 100 billion and 400 billion stars. Around most of those stars, there are planets. Around many of those planets, there are moons, and scattered across billions of those worlds, across timescales we cannot fully comprehend. Chemistry has had every opportunity to do what chemistry does here on Earth, to organize itself, to replicate itself, to grow more complex over time, to become something that thinks. The math, when you do it, is not close. It is not a matter of uncertainty. By any rational calculation, by any honest application of probability, the universe should be absolutely crowded with life. Not just microbial life, not just single-celled organisms clinging to the underside of rocks. Intelligent life. Technological civilization. Species that have had millions or billions of years longer than us to develop, to spread, to build, to communicate across the void. And yet, silence. The night sky, when you listen to it, really listen to it, with the most sensitive instruments humanity has ever constructed pointed outward across every frequency we know how to detect, is almost perfectly, completely, unnervingly quiet. No signals, no beacons, no megastructures blocking the light of distant stars in any pattern we can explain with geology or physics. No laser pulses aimed in our direction from civilizations trying to announce themselves. No signatures in the microwave background that suggest something engineered it. No gravitational wave patterns that look like something deliberate. Nothing in the X-ray band, nothing coherent in radio, nothing structured in infrared that doesn't resolve into a natural explanation when you look hard enough. Just the hiss of cosmic background radiation, the random chatter of pulsars, the occasional burst from a magnetar, natural, cold, indifferent processes running on schedule, accountable to no intelligence. Where is everyone? That question was first articulated, at least in the way we now frame it, by a physicist named Enrico Fermi in 1950. He was having lunch at Los Alamos National Laboratory with colleagues, and somewhere between the cafeteria line and a conversation about flying saucers in the news, he looked up and said something to the effect of, "But where are they?" The exact words are disputed. The weight of the question is not what Fermi understood, intuitively and immediately, was the tension between the scale of the universe and the absence of any evidence for anyone in it. He was a physicist who had spent years working on timescales and probabilities. He understood that if civilizations arise with any regularity across the galaxy, and if any of them develop technology even remotely like ours, the numbers work out in a way that should have produced visible, detectable, undeniable evidence of their existence long before any of us were born. The galaxy is old, older than Earth by billions of years. A civilization that got a head start of even 50 million years, a rounding error in cosmic time, would have had time to colonize every star in the Milky Way, many times over, using nothing more exotic than the physics we already know. But there is nothing. The sky is quiet, the radio bands are clean. The cosmos, for all its staggering size and age, looks exactly as it would look if we were the only ones here. This is called the Fermi Paradox. And in the 75 years since that lunch, it has not been resolved. Every serious attempt to answer it has either required special pleading, uncomfortable assumptions about human uniqueness, or conclusions so dark that most people who encounter them prefer to look away. This is the story of why the universe might be quiet. And it is not the story most people expect. It is tempting when you first encounter the Fermi Paradox to assume the answer is simple. Maybe life is just rare. Maybe we got lucky. Maybe the conditions that gave rise to biology on Earth are not as common as the planet count suggests. Maybe the leap from chemistry to life is genuinely hard, so hard that it happened here once in the entire history of the galaxy, or close to it. Maybe we are an accident so improbable that the universe is, in a meaningful sense, ours alone. This is a comforting answer. It is also, at every level of analysis, becoming harder to defend. In the last 30 years, the field of astrobiology has transformed from a speculative backwater into one of the most active areas of science. We have found planets around nearly every star we have examined closely. Not just rocky planets at the right distance from their star for liquid water, though we have found those too in the hundreds, but planets in conditions that range so widely across the possible spectrum of habitable environments that the old assumption of life needs exactly what Earth has been almost completely abandoned. We have found liquid water on moons of Jupiter and Saturn. We have found complex organic chemistry in interstellar space drifting between the stars. We have found amino acids in meteorites. We have found conditions under which extremophiles, organisms here on Earth that evolved in environments once considered universally lethal, can survive temperatures, pressures, radiation levels, and chemical compositions that would have seemed laughably inhospitable a generation ago. The building blocks of life are not rare. They are, by any measure we have, promiscuously abundant. Carbon, the backbone of every biology we know, is one of the most common elements in the universe. Water is everywhere. The basic chemistry of replication, the tendency of certain molecular structures to make copies of themselves, has been demonstrated in laboratory conditions mimicking the early Earth, the early Mars, the subsurface oceans of icy moons, even interstellar space. So if the ingredients are everywhere, and the timescales are vast, and the number of potential locations is astronomical, then the silence becomes not a comfortable resolution, but a profound, pressing, almost intolerable mystery. The quiet sky is not a relief, it is a clue, and the clue points somewhere that most people, when they follow it honestly, find genuinely disturbing. There is a concept in this field called the Great Filter. It was first articulated in detail by the economist Robin Hanson in a 1998 paper that, for something published in an academic journal about an abstract problem in astrobiology, has had a remarkable and almost unsettling cultural afterlife. The idea is not complicated, but its implications are devastating. The Great Filter is whatever it is that keeps the universe quiet. If intelligent technological civilizations should be common, and the math suggests they should, and they are not detectable, and the evidence suggests they are not, then something is filtering them out. Something is preventing the universe from filling up with the kind of life that builds radio transmitters and generation ships and Dyson spheres. Something is stopping civilizations from reaching the point where they would leave the kind of marks we should be able to see. That something is the Great Filter. Now, the filter could be behind us. It could be something we have already passed through. The origin of life itself, for instance, might be extraordinarily difficult, not just unlikely, but vanishingly, almost impossibly rare. The jump from non-life to self-replicating chemistry might require a combination of conditions so precise that it happens only once every trillion planets, or once per galaxy, or once per Hubble volume. If that is the case, then we got through the filter already. We are the winners of an almost incomprehensible lottery. And the silence is explained, not because intelligence is filtered out later, but because it almost never gets started. Alternatively, the emergence of the eukaryotic cell, the complex, nucleus-containing cell type that is the ancestor of every plant, animal and fungus on Earth, might be the filter. This transition from simple prokaryotic life to complex eukaryotic life took roughly 2 billion years here on Earth, despite a planet already teeming with microbial life. It may be a transition so difficult, so dependent on a specific series of molecular accidents, that it almost never happens, or the filter might be consciousness itself. The development of a nervous system, a brain, self-aware cognition, the capacity to model the world and ask questions about it. This might be the hard step. Simple life might be common. Complex multicellular life might be relatively common. But the specific architecture of intelligence, of the kind that leads to technology, might be extraordinarily rare, even given billions of years of evolution to work with. Each of these possibilities, if true, would explain the silence. And each of them, if true, is genuinely wonderful news. It means we are special. It means we survived something almost no one survives. It means the future is, in some sense, ours. But there is the other possibility, the one that sits at the back of every serious treatment of the Fermi Paradox and refuses to be dismissed, the one that explains the silence just as cleanly, with just as much logical rigor, but in a way that offers no comfort at all. What if the filter is ahead of us? What if the thing that silences civilizations is not some improbable step in biology or chemistry, but something that happens to technological species after they develop? What if the silence is not the sound of life failing to start, but the sound of civilizations that started, flourished, reached our level or beyond, and then went quiet for a reason that has nothing to do with their uniqueness or their luck? What if the reason the universe is quiet is that every civilization capable of making noise eventually stops making noise permanently? This is the uncomfortable version. This is the version that, once you understand the mathematics behind it, makes it very hard to look at our current moment in history without a certain involuntary chill. Because if the filter is ahead of us, then the silence of the universe is not evidence of our rarity. It is a warning, a pattern, a regularity that says, all roads lead here. In 1977, a researcher named Jerry Amon was working as a volunteer for SETI, the Search for Extraterrestrial Intelligence, at Ohio State University. He was reviewing computer printouts of radio telescope data from a survey of the sky, looking for signals that stood out from the cosmic noise. And he found one. A signal that was, by every measure he had available, exactly what a transmission from an extraterrestrial intelligence would look like. It came from the direction of the constellation Sagittarius. It lasted 72 seconds, the full window the telescope could track a fixed point in the sky. It was transmitted at a frequency very close to 1,420 megahertz, the frequency of neutral hydrogen, which is the most common element in the universe and had been theorized as a natural channel for interstellar communication. A frequency any technologically capable civilization would know, a kind of cosmic common denominator. for radio communication. The signal was so dramatically out of place, so clean against the background noise, so unlike anything Ayman had seen in all his hours of data review, that he circled it on the printout with a red pen and wrote a single word in the margin. Wow! It was never detected again. Every attempt to find it, and there have been many with increasingly powerful instruments over nearly 50 years, has returned nothing. The wow signal appeared once, lasted 72 seconds, and vanished. Its origin has never been definitively explained. Natural explanations, comets, hydrogen clouds, satellite interference have been proposed and variously disputed. The honest scientific position, which most researchers in the field will admit if pressed, is that we do not know what it was. But the wow signal is not the reason this story matters. It matters because of what it represents. The single, most compelling piece of potential evidence we have for the existence of another communicating civilization, and it came with no follow-up, no continuation, no context, just a flash of organized radio frequency out of the dark, and then silence again. The universe gave us one possible hello, 7 seconds shy of a minute and a half, 49 years ago, and then resumed its perfect, infuriating quiet. There is a particular kind of intellectual vertigo that comes from sitting with these facts all at once. The scale of the universe, the abundance of its ingredients, the billions of years it has had to work with, the mathematical inevitability, given all of that, of technological civilization. And then the silence, the absolute, total, near-perfect silence. Something is wrong with the picture. Either the universe is far less hospitable to life than it appears, in which case we are a miracle, or something happens to civilizations that makes them stop being visible, in which case we are a civilization with a countdown we may not be able to see. Both possibilities have been studied seriously. Both have proponents. Both generate predictions that we are, slowly, beginning to have the tools to test, and neither of them leads anywhere comfortable. What this series is going to do is something that most treatments of the Fermi Paradox avoid. They tell you the question. They list the possible answers. They let you sit with the ambiguity. They frame it as a philosophical puzzle, a fun thought experiment, a cosmic mystery with no particular urgency. This is not that. This is a countdown, not to an alien signal, not to a definitive answer, but to the moment when the Fermi Paradox stops being a question about what exists out there and becomes a question about what we are doing right here, right now, and how much time we have left to do it differently. Because the silence of the universe has a shape, it has a structure, and when you examine that structure carefully, when you look at the ways civilizations could go quiet and the time scales over which it tends to happen, and the patterns in our own history that rhyme a little too closely with the theories, the picture that emerges is not a mystery. It is a mirror. The universe is quiet, and the reasons it might be quiet are, one by one, things we can see the beginnings of in ourselves. That is the part nobody wants to talk about. That is the part we are going to talk about. We are going to start at the beginning with the Drake equation, which is the formalized version of Fermi's lunchtime question, and with what we have learned about its variables in the 70 years since Frank Drake first wrote it on a blackboard in 1961. Because the equation is not just a historical curiosity, it is a diagnostic tool. Each of its variables is a stage in the development of a civilization, and each of those stages represents a possible location for a filter. And when you map those variables against what we now know about the universe and about the abundance of planets, about the frequency of biosignatures in our solar system, about the nature of intelligence and technology, the equation does not resolve the paradox. It sharpens it. It makes the silence louder. Frank Drake was 30 years old when he organized the first systematic scientific search for extraterrestrial intelligence, a project called OSMA, using an 85-foot radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia. He pointed the dish at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for about 200 hours across the spring and summer of 1960. He heard nothing useful. A signal that caused brief excitement turned out to be a secret military aircraft broadcasting on a frequency it shouldn't have been. The next year, Drake convened a meeting at Greenbank with a small group of scientists to discuss the question seriously. To structure the conversation, he wrote down on a blackboard the factors that would need to be estimated to calculate how many communicating civilizations might exist in the Milky Way at any given time. The equation he wrote has been refined and debated ever since, but its structure has remained essentially the same. You start with the rate at which stars form in the galaxy. You multiply by the fraction of those stars that have planets, then the fraction of those planets that could support life, then the fraction on which life actually develops, then the fraction on which intelligent life develops, then the fraction of intelligent civilizations that develop technology capable of communication across interstellar distances. And finally, and this is the variable where everything either opens up or collapses, you multiply by the average length of time such a civilization remains detectable. That last variable is called L, and L is where the silence lives. If L is large, if civilizations, once they develop communication technology, tend to survive and transmit for millions or billions of years, then the galaxy should be full of signals. The math is almost embarrassingly clear on this point. Even with conservative estimates for every other variable, a large L floods the galaxy with detectable signatures. We should have found something by now. If L is small, if civilizations tend to go quiet after only a few hundred or a few thousand years, then the silence is explained. The galaxy could have hosted thousands or millions of technological civilizations across its history. Some of them might have been extraordinary, some of them might have reached levels of capability that we cannot currently imagine. But if each of them, on average, remained detectable for only a cosmically brief window, then at any given moment the galaxy would look almost empty. L is the great filter, hiding inside a variable, and here is the thing about L that tends to make people quiet when you say it out loud. We have exactly one data point for how long a technological civilization tends to remain detectable. We have ourselves. And we have been transmitting, producing what are called technosignatures, electromagnetic signals that differentiate our planet from a purely natural one, for approximately 120 years. 120 years out of a galaxy that is 12 billion years old. We do not yet know if we are going to make it to 200. We do not know if the things we are currently doing to our atmosphere, to our social fabric, to our nuclear arsenals, to the climate systems that allow this biosphere to support 8 billion people. We do not know if those things are problems we will solve or the beginning of our own contribution to the silence. That question, that specific, terrible, close question, is what sits at the heart of everything that follows, not as a political argument, not as a moral lecture, but as a scientific and probabilistic reality that the Fermi Paradox keeps pointing toward, like an arrow that never quite points anywhere else. The universe is quiet. The question is whether we are the rare ones who got through everything that silences civilizations, or whether we are right now in the phase that precedes going quiet. We are going to examine every serious hypothesis that attempts to explain the silence. We are going to look at them not as philosophical positions to be held or rejected, but as countdown models, as ways of understanding when and why the noise stops. We are going to look at what they predict. We are going to look at how those predictions map onto what we can observe. And at the end, we are going to sit with the version of this story that the evidence, taken seriously, most strongly supports. Not the version that feels best, the version that fits, because the universe is quiet for a reason, and it isn't what most people think it is. Let's begin with the most optimistic explanation for the silence, because it deserves a fair hearing before we dismantle it. The rare Earth hypothesis holds that the conditions required for complex, multicellular, intelligent life are not merely uncommon, they are extraordinarily, almost uniquely specific. That Earth, far from being an average planet around an average star in an average galaxy, is the product of a staggering chain of coincidences so long and so improbable that it may have occurred only once in the observable universe, or close to it. That when we look out at all those billions of galaxies and trillions of planets and feel the mathematical weight of the numbers pressing toward a conclusion that life should be everywhere, we are making an error. The error of assuming that what happened here is the kind of thing that happens rather than the kind of thing that almost never happens and yet, given enough tries, happened once. The rare Earth hypothesis was formalized in a book of the same name published in 2000 by paleontologist Peter Ward and astronomer Joe Kirschvink. Their argument was detailed and serious, and it deserves to be engaged with on those terms, because the version of it that tends to circulate in popular discussion is a simplified caricature of the actual case they made. Their argument was not simply that Earth is in the right place, it was that Earth is in the right place in multiple independent and compounding ways simultaneously, and that the probability of all those factors coinciding by chance on a single planet is, when you work through the arithmetic, genuinely tiny. Consider the list. Earth orbits in the habitable zone of its star, far enough for water to remain liquid, close enough to retain heat. But not just any star. The Sun is a G-type main sequence star of unusual stability. Many stars are variable. They flicker, they flare, they produce UV radiation at levels that would strip the atmosphere from any nearby planet before biology had a chance to get started. The Sun, by contrast, has been producing almost exactly the same amount of energy, with almost no variation, for 4.5 billion years. This is not typical, it is, in stellar terms, unusually well behaved. Earth also has a large moon, disproportionately large for its size. The moon is about a quarter the diameter of Earth, which is almost unheard of in the ratio of satellite to planet. And the moon does something that may be deeply important for the development of complex life. It stabilizes Earth's axial tilt. Without the moon's gravitational influence, Earth's axis would wobble chaotically over millions of years, producing climate swings so extreme that the evolution of anything beyond microbial life might be perpetually interrupted. Mars, which has no large moon to stabilize it, has had its axial tilt swing between near zero and over 60 degrees across its history. The climate consequences are catastrophic. Earth, with the Moon, has stayed within a narrow band of axial stability for long enough that complex life could evolve, diversify, and eventually produce something that builds telescopes and asks why the sky is quiet. There is also Jupiter. The gas giant sits in the outer solar system in an orbit that, for most of Earth's history, has acted as a gravitational vacuum cleaner, deflecting or capturing comets and asteroids that would otherwise rain down on the inner planets at a frequency that would make sustained biological complexity nearly impossible. The debate about Jupiter's precise net effect has grown more complicated in recent years. Some models suggest it also throws material inward rather than only deflecting it outward. But the baseline point remains that the specific architecture of our solar system, with its outer gas giants and its clear inner zone, is not generic. Many planetary systems we have observed are architecturally very different. Add the galactic location. Earth sits in what is called the galactic habitable zone, far enough from the densely packed, radiation-saturated galactic center that sterilizing supernovae events are rare, but close enough to the galactic disk that heavy elements forged in previous generations of stars are abundant enough for rocky planet formation and for the complex chemistry that life requires. Too far out toward the galactic edge and you are in a region metal-poor enough that rocky planets may not form at all. Too far in and the radiation environment becomes genuinely lethal at the planetary surface, and then there is plate tectonics. Earth's crust is divided into moving plates that cycle material between the surface and the interior, a process that, among many other consequences, regulates the carbon dioxide concentration of the atmosphere over geological timescales, acting as a planetary thermostat that has kept Earth from freezing over or overheating for billions of years despite significant changes in the Sun's output. Not all rocky planets have plate tectonics. Mars does not. Venus does not. Whether a planet develops tectonic activity seems to depend on its size, its internal heat, the composition of its mantle, factors that are not universally shared. If you require all of these conditions simultaneously, stable star, large moon, gravitational shield in the outer system, galactic habitable zone location, tectonic carbon cycle regulation, the probability of any given planet satisfying all of them at once begins to look very small indeed. Multiply enough small probabilities together and you get a number that could be less than 1, meaning less than 1 planet in the observable universe meets every criterion. The rare Earth hypothesis is internally coherent. It is supported by real scientific data. And it is almost certainly partially correct. Some of these factors do matter, and their combination is not universal. But there are serious problems with taking it all the way to the conclusion that we are alone, or nearly alone. The first problem is that the hypothesis requires us to believe that every factor we have identified as important for life on Earth is necessary for life in general, that there is no other way to produce complex biology under different conditions. This assumption has been weakened repeatedly and significantly by advances in astrobiology over the last 2 decades. We have found life on Earth in conditions that, 30 years ago, would have been considered absolutely incompatible with biology. Organisms living in the crushing pressure of deep ocean trenches, in the boiling water of hydrothermal vents, in the hypersaline pools of Antarctic ice sheets, inside solid rock kilometers below the surface. Life, it turns out, is not as narrowly constrained as the rare Earth hypothesis needs it to be. The second problem is the discovery of subsurface liquid water in our own solar system, on Enceladus, on Europa, quite possibly on several other moons of the outer planets. These environments have no sunlight, no surface liquid water, no plate tectonics, no large stabilizing moon, and yet they are not considered uninhabitable. They are, in fact, considered among the most promising targets in the search for extraterrestrial life within our own solar neighborhood. If life can potentially exist there, environments radically different from the surface of Earth, then the surface of Earth is not the template. It is just one template. The third problem is the most fundamental. Even if you accept every constraint the rare Earth hypothesis proposes, you are multiplying probabilities against a denominator that is almost incomprehensibly large. There are, in the observable universe alone, somewhere between 1 sextillion and 10 sextillion stars. That is a 1 followed by 21 to 22 zeros. Even a probability of 1 in a quadrillion, 1 in 10 to the 15th power, applied to that denominator produces millions of potential Earths. The universe is so large that even genuinely rare events happen many, many times. So the rare Earth hypothesis can explain why life is uncommon. It cannot easily explain why the galaxy, which is 12 billion years old and contains 400 billion stars, shows no signs at all of having produced even a single civilization that left detectable traces. Even rare things, given enough time and enough tries, leave evidence. This brings us to a different category of explanation. Not one that says life is rare, but one that says life is out there, perhaps abundant and simply not talking to us. Or not in a way we can hear, or not for reasons that are innocent. The zoo hypothesis was proposed in 1973 by the radio astronomer John Ball. His suggestion was that the silence is deliberately maintained, that technologically advanced civilizations are out there, aware of us, and have collectively agreed, or perhaps been instructed by some governing intelligence, to leave us alone. That we are the animals in a cosmic zoo, observed but not contacted, protected from interference until we reach some threshold of development, after which the silence will end, and the universe will introduce itself. The zoo hypothesis is psychologically satisfying in a particular way. It preserves the sense that we are not alone. It offers a future moment of contact, a graduation day of sorts. It is, at its heart, a story about being watched over. It is also, scientifically, nearly unfalsifiable and therefore nearly useless as a hypothesis, and its internal logic begins to collapse under examination almost immediately. The core problem is what's called the uniformity problem, sometimes called the monocultural fallacy. The zoo hypothesis requires that every single technologically capable civilization in the galaxy, across billions of years of independent development, each with its own history and culture, and values and motivations, has independently arrived at or been compelled into the same policy regarding Earth. Not most of them, all of them. Because one civilization that didn't follow the protocol, one curious rogue intelligence that decided to break ranks and say hello, would be enough to end the silence. In human history, we have never seen any collective of independent actors maintain a perfect consensus indefinitely on anything. The idea that hundreds or thousands of independent civilizations, each arising separately across different stars and timescales, would all agree to the same hands-off policy toward Earth and maintain it without exception across the entire period of our development requires a level of coordination or coercion that itself demands explanation. Who enforces the silence? If it is voluntary coordination, why hasn't a single civilization deviated? If it is enforced by some dominant power, then that dominant power should itself be detectable. A civilization with the reach and capability to police the behavior of every other intelligence in the galaxy would be exactly the kind of thing our instruments should be finding. The zoo hypothesis escapes one problem only by creating a larger one. There is a variant of this idea that avoids some of the coordination problems by moving the silence producer inward rather than outward. It is called the planetarium hypothesis, and it was proposed by the philosopher and SETI researcher Stephen Webb in a somewhat different form, though variations of it have circulated for decades. The idea, stated bluntly, is this. What if the universe we observe is not the real universe? What if the empty sky, the absence of signals, the apparent isolation of humanity is not a feature of an actually empty cosmos, but of a simulation or a controlled environment designed to present the appearance of emptiness to us specifically? This idea tends to get dismissed quickly because it sounds like science fiction. But it is worth engaging with briefly because it represents a genuine logical response to the paradox. If the silence is perfect, and if nothing we do can break it, then one explanation is that the silence is constructed, that whoever or whatever is running the environment has included the appearance of emptiness as a design feature, either to protect us, to study us, or for reasons we cannot access. The honest answer about the planetarium hypothesis is that it is not scientifically testable in any conventional sense, and therefore it sits at the boundary of what we can productively discuss. We will set it aside, not because it is impossible, but because it leads nowhere useful. If the silence is artificial and total and we cannot break it from inside, then the question of why we should study the Fermi Paradox at all dissolves. We will assume, as scientists must, that the universe we observe is the universe that exists, and in that universe the silence is real and it is waiting for an explanation. The next category of explanation is more recent, more specific, and considerably more unsettling. It comes not from an astronomer or a biologist or a physicist, but from a science fiction author, though the ideas within it are grounded in game theory, evolutionary biology, and the logic of survival under conditions of irreducible uncertainty. The dark forest hypothesis takes its name from a passage in the second novel of Chinese science fiction author Liu Cixin's three-body problem trilogy, published in 2008. The image Liu uses is this. Imagine a dark forest. Every hunter in the forest is armed. Every hunter knows that every other hunter is armed. Every hunter knows that every other hunter is trying to survive. And every hunter knows that if another hunter detects them, they cannot be certain of that hunter's intentions. And the cost of being wrong, of assuming a strange hunter is friendly when they are not, is death. In a dark forest, the rational strategy is to move silently. And if you detect another presence, another fire, another footstep, another sound in the trees, the rational strategy is not to approach, not to call out, not to wait and see. The rational strategy is to extinguish it before it can extinguish you. This is a theory of the Fermi Paradox. The universe is quiet because every civilization that is capable of making noise has independently reasoned its way to the same conclusion. That announcing your existence in a universe of unknown and potentially hostile intelligences is suicidal. That the silence is not absence, it is camouflage, and that any civilization that breaks that camouflage, that broadcasts its location, its capabilities, Its nature across the void is doing something that natural selection operating at the civilizational level would rapidly eliminate. The great silence on this model is not the sound of civilizations failing to arise or failing to survive. It is the sound of civilizations that survived by learning to hide, and here is the part that closes the loop in a way that makes the wow signal feel different the second time you think about it. If the dark forest hypothesis is correct, then the silence we observe is the equilibrium state of a mature galaxy, a galaxy that has had enough time for civilizations to arise, communicate briefly, get burned for it, and learn. A galaxy that has had enough time for the lesson to be encoded not culturally, but perhaps more deeply. A galaxy where the silence is now maintained not by choice but by something closer to instinct, the survival signature of every intelligence that made it past a certain threshold. And if that is true, then the wow signal is not a friendly hello. It is either a mistake, a leak from a civilization whose camouflage briefly failed, or something more deliberate and more troubling, a probe, a test. An identification pulse designed not to initiate communication but to map which locations in the galaxy respond. We did not respond to the wow signal, partly because we didn't detect it in real time, and partly because even after we identified it, no single agreed response was issued. The silence on our end was accidental and uncoordinated, but in a dark forest framework, our accidental silence may have been the correct response, and our decades of broadcasting into the sky, the early television signals, the radio waves, the deliberate messages we have aimed at nearby stars, including a transmission sent toward the globular cluster M13 in 1974, may have been exactly the kind of thing that marks a civilization as young, naive, and unaware of the rules of the forest. The first rule of which is, do not let anyone know you are there. Now, it is important to be honest about the dark forest hypothesis. It is not a scientific theory in the formal sense. It does not make specific, testable, falsifiable predictions in the way that a good scientific hypothesis should. It is a logical framework, a set of premises about game theory and survival under uncertainty that, if the premises are true, would predict the observed silence. But we cannot directly test whether the premises are true. We cannot verify that other civilizations exist, or that they reason this way, or that the forest analogy actually describes the social dynamics of interstellar space. There are also serious objections to the hypothesis on its own terms. The most fundamental is that it assumes a level of paranoia and zero-sum competition that may not universally apply to all possible intelligences. The game theory of the dark forest depends on a key premise, that civilizations cannot reliably determine the intentions of other civilizations at interstellar distances, and that the cost of assuming benevolence when faced with malevolence is catastrophically high. Both of these premises are reasonable, but they are not inevitable. A civilization advanced enough to survive in Liu's forest for billions of years might have developed communication or detection abilities that allow them to assess intention at a distance. They might have social structures or value systems that weight the risk of wrong kind preemptive killing differently than human game theory would suggest. But here is the thing about the dark forest objections. They require that every civilization in the galaxy, or at least every civilization that did not go quiet for some other reason, independently came to the conclusion that the risk-benefit analysis favors disclosure over silence. They require that no civilization across the vast sweep of galactic history has acted on the logic of preemptive elimination. They require that the default state of interstellar civilization is cooperation and benign curiosity rather than competitive survival. We have exactly one example of a technological civilization to look at, and that civilization, ours, has a history in which first contact between a technologically superior and technologically inferior group has, with essentially no exceptions, been catastrophic for the inferior group. Not because the superior civilization was uniquely evil, but because the logic of a resource competition and survival advantage tends to produce certain behaviors when two groups meet, and those behaviors do not historically favor the weaker party. This does not prove the dark forest hypothesis, but it does suggest that the assumption of universal cosmic benevolence requires more support than it typically receives from those who dismiss the dark forest too quickly. We are now at a crossroads in the analysis, standing between two broad categories of explanation for the silence. On one side, filters that operate before civilization, eliminating the possibility of detectable life before it arises. On the other, filters that operate after civilization, ending or suppressing detectable life once it appears. In the middle, complicated and overlapping hypotheses about deliberate concealment, about the nature of communication, about the possibility that we are simply not listening in the right way. We are going to go somewhere that most treatments of this subject avoid for as long as possible. We are going to stop looking outward at the theoretical landscape of alien civilizations and start looking inward at our own trajectory, our own timeline, our own position in the Drake equation, because the most important variable in the Fermi paradox is not one about alien life. It is the one about L, about duration, about how long a civilization like ours tends to persist once it crosses the threshold into the technological age. And when you look at L honestly, when you look at every mechanism that has been seriously proposed for why technological civilizations go quiet, and then look at our own civilization's current behavior, the number you arrive at is not comforting. We will look at what extinction-level risks actually look like when they are mapped against civilizational development timelines. We will look at what the Fermi paradox implies not about the past of alien civilizations, but about our own near future. And we will look at the specific, measurable, countdown-shaped nature of the threats that currently define our position in the equation. Because the universe is quiet, and the silence, examined carefully, sounds less like an absence and more like a pattern that begins to look, the longer you study it, disturbingly familiar. There is a particular kind of clarity that comes from looking at your own civilization, the way an astronomer looks at a distant star. Not with hope or fear or political conviction, but with the cold, measuring eye of someone trying to understand a physical process. To ask not, what should we do, but what does the pattern suggest? To treat humanity not as the protagonist of history, but as a data point in a much larger equation, one variable among several, in a formula that has been running across the galaxy for billions of years without us, and will continue running long after we are either gone or transformed into something unrecognizable. When you do that, when you step back far enough to see the shape of what we are and where we are in our own development, a few things become immediately, uncomfortably clear. The first is that we are young, almost insultingly young by the standards of what the universe has had time to produce. The Earth is 4.5 billion years old. Complex multicellular life has existed for roughly 600 million years. Our genus, Homo, has been around for perhaps 2 to 3 million years. Our species, Homo sapiens for roughly 300,000, agriculture and settled civilization, the precondition for everything we think of as human history for perhaps 12,000 years. Industrial technology, the thing that makes us detectable from space for approximately 200 years. Nuclear weapons, the first technology we developed that was capable of ending our civilization in a matter of hours for about 80 years. 80 years. In a galaxy 12 billion years old. In a universe 13.8 billion years old. We have been capable of self-annihilation for a period of time that is, relative to the age of everything, essentially instantaneous. We are, in the most precise sense, a newborn civilization holding, for the first time, a weapon it does not fully understand and has not yet decided it knows how to put down. This is not a political observation, it is a data point. And when you place that data point alongside the structure of the Fermi Paradox, alongside the question of what L looks like for technological civilizations in general, it generates a specific and measurable anxiety. If the great filter is ahead of us, it is not because alien civilizations ran into some exotic physics problem or encountered some bizarre cosmic hazard that we would have no way to anticipate. The proposed mechanisms for civilizational collapse that appear most frequently in serious academic literature are not exotic at all. They are, almost without exception, things we already recognize. Things we are already watching develop. Things we have, in several cases, already come close to triggering. Let us go through them in order of the timescales involved, from the most immediate to the more extended. Not because ranking them by immediacy tells us which is most dangerous, but because understanding the countdown structure of each one is essential for understanding what our position in the Drake equation actually looks like. The most acute risk, the one that operates on the shortest possible timescale, the one that could in principle end the experiment of human civilization within the span of an afternoon, is nuclear weapons. As of the time this is being written, there are approximately 12,500 nuclear warheads distributed across 9 countries. Approximately 3,700 of those are deployed, positioned on delivery systems ready to be launched. Of those deployed weapons, approximately 1,800 are kept on what is called high alert, meaning they can be launched within minutes of a command decision. The combined yield of the global nuclear arsenal, if deployed against population and infrastructure targets, would be sufficient to kill hundreds of millions of people directly and to trigger a nuclear winter, a global climate disruption driven by soot and ash injected into the upper atmosphere by firestorms, severe enough to collapse agriculture across the planet for years. The secondary death toll from starvation and societal breakdown in a full nuclear exchange between the largest arsenals would, by the estimates of researchers who study this, be measured in billions. This is not speculation. The physics of nuclear winter has been modelled extensively since the 1980s, refined with increasingly sophisticated climate simulations, and the core findings have remained stable across decades of independent research. A large nuclear exchange would not just kill the people it directly kills. It would destabilize the climate systems that support global food production for long enough that civilizational recovery would be deeply uncertain. What is notable about nuclear weapons from the perspective of the Fermi Paradox is not just their destructive capacity. It is the combination of their capacity and the structural conditions under which they are maintained. The modern nuclear deterrent system, the framework of mutually assured destruction that has, so far, prevented their use in war since 1945, is not a stable equilibrium. It is a dynamic, fragile system that depends on clear communication between adversaries, on the accurate interpretation of sensor data, on the psychological stability and sound judgment of a small number of decision makers, and on the absence of accidents. All of these dependencies have, at various points in the last 80 years, come within striking distance of failing. In 1983, a Soviet satellite early warning system incorrectly identified a reflected sunlight pattern as an incoming American missile launch. The duty officer responsible for reporting the alert to his superiors, a man named Stanislav Petrov, judged it to be a false alarm based on his own intuition. The logic that the Americans, if launching a first strike, would not begin with a single missile. He did not report the alert up the chain of command. He was correct. It was a malfunction. Had he followed procedure, the launch of Soviet retaliatory missiles might have been ordered before anyone had time to verify the data. In 1995, a Norwegian scientific rocket launched to study the aurora borealis was briefly detected by Russian radar as a possible submarine-launched ballistic missile. Russian President Boris Yeltsin was notified, and the nuclear briefcase was activated, the first and only time in history that a Russian leader had the briefcase open with a launch decision in progress. The rocket's trajectory resolved as non-threatening before any decision was made. The incident lasted several minutes. These are not the only incidents of this kind, they are two of the most documented. There is a body of declassified material slowly expanding across decades of freedom of information requests and archive releases that suggests the near-miss history of nuclear deterrence is considerably more populated than the public narrative typically acknowledges. The countdown implied by this situation is not a countdown to a planned event. It is a statistical one. If the probability of accidental or miscalculation-driven nuclear exchange is, say, 1% per decade, and serious researchers who study this question suggest that estimate is not unreasonable, then across a century the cumulative probability of such an event is approximately 10%. Across 2 centuries, approaching 20%. These are not negligible probabilities for the continued existence of a technological civilization, and this is before accounting for the possibility of deliberate use, for future conflicts between nuclear states, for the potential acquisition of nuclear capability by non-state actors, for the dynamic instability introduced by new nuclear powers entering a deterrence framework not designed with them in mind. From the perspective of L in the Drake equation, nuclear weapons represent a filter that activates at a very specific moment in civilizational development. The moment a species first acquires the ability to split the atom and control a chain reaction. It is a filter that gives you a window. The window is the period between acquiring the weapon and either eliminating it or destroying yourself with it. That window for civilizations that don't make it through may be measured in decades to a few centuries, which, on a galactic timescale, is exactly the kind of L that would explain why we don't see anyone. But nuclear weapons are not the only countdown running. They are not even, by some measures, the most likely mechanism of civilizational disruption in the near term. They are simply the most acute, the one with the shortest possible timeline to catastrophe if something goes wrong. The second major filter mechanism that appears repeatedly in serious analysis of civilizational risk is climate change, not in the simplified political framing in which it usually appears in public discourse, but in the full systems dynamic sense. The disruption of the atmospheric and oceanic systems that have, across the last 10,000 years provided the stable, predictable climate envelope within which human agriculture, settlement patterns, and civilization developed. The timeline here is slower. It is measured in decades to centuries rather than minutes to years, but the risk profile is, in some ways, more structurally threatening precisely because of its slowness, because it operates across a time scale that is long enough to allow repeated deferral of response, to allow each generation to pass the problem forward, to allow the slow accumulation of consequences to remain below the threshold of crisis, level response until the feedback loops that could accelerate it become locked in. The scientific picture on the mechanisms of severe climate risk is well established, and we are not going to spend this time on the basic physics of radiative forcing. What matters for the Fermi Paradox framing is the structure of the risk and the question of whether it represents a universal feature of technological civilization, a filter that doesn't just threaten us, but would threaten any civilization that goes through an industrial phase. The answer is almost certainly yes. Any civilization that develops technology at the pace we have will almost inevitably pass through a phase of intensive energy consumption driven by carbon-based fuels, for the simple reason that carbon-based fuels are energetically dense, geologically abundant, and technically accessible with early industrial technology. The alternative energy sources that can replace them, nuclear fission, solar photovoltaics, fusion, whatever comes after, require more advanced materials science, engineering infrastructure, and scientific understanding. They become accessible later in the development curve. This means that the window of heavy carbon burning is not specific to Earth. It is not a mistake we made. It is a phase of development that follows almost necessarily from the sequence of technological discovery, from fire to coal to oil, to the beginning of a transition away from combustion that requires civilization to have already accumulated enough scientific and industrial capacity to build the alternatives at scale. Every civilization that developed technology from a starting point of animal and plant chemistry would likely go through this phase. And every civilization that went through this phase would face some version of the climate disruption it causes. The question is whether the disruption is managed, whether the transition to the alternative energy systems happens fast enough to prevent the feedback loops that could push the climate into a state that is genuinely incompatible with the kind of organized, stable, high-energy civilization required to continue building technology, or whether the disruption accumulates beyond the management threshold. The specific feedback loops that researchers flag as most concerning in the long-term scenario are well documented. Permafrost thaw releasing stored methane, a greenhouse gas far more potent than carbon dioxide on short timescales. Ice sheet loss reducing the planet's reflectivity and accelerating warming. Forest dieback converting carbon sinks into carbon sources. Ocean circulation changes disrupting the regional climate patterns on which agricultural systems depend. These are not catastrophic in the nuclear sense. They do not end civilization in an afternoon, but if allowed to lock in, they could produce a planet that is, over centuries, significantly less capable of supporting the kind of complex, stable, organized civilization required to continue a technological trajectory. From an L perspective, the climate filter doesn't necessarily kill a civilization, but it may reliably knock civilizations down, set them back, reduce their complexity, break the continuity of their scientific and technological development at critical moments. A civilization that loses several centuries to climate instability during what should be its fastest period of technological growth is a civilization that may never develop the tools needed to escape the solar system, to detect or prevent asteroid impacts, to solve the next generation of existential problems on the list. The third countdown is different in character from the first two. It is not a product of any specific technology or any particular phase of development. It is a feature of the information architecture of advanced civilization, a problem that appears to be waiting at a certain level of technological capability for any intelligence that reaches it. In the last 3 decades, humanity has developed the ability to design and engineer biological organisms, to read the code of life and, increasingly, to write it. To take the machinery of replication and mutation that drives evolution and operate it deliberately, at speed, producing results that natural selection would have taken millions of years to arrive at, or might never have arrived at all. This is the revolution in synthetic biology and genetic engineering, and it is advancing at a pace that continues to exceed most projections. The same capabilities that make it possible to engineer organisms to produce insulin, to develop vaccines at unprecedented speed, to potentially cure genetic diseases, also make it possible, increasingly, within the reach of smaller and smaller groups of people, to engineer organisms designed to be dangerous, to take the basic machinery of a pathogen and modify it in ways that increase its transmissibility, its lethality, its resistance to treatment. The COVID-19 pandemic provided a preview of what a naturally arising respiratory pathogen of moderate severity and high transmissibility can do to global civilization in a matter of months. And that was a pathogen that killed, by most estimates, somewhere between 0.5 and 1.5% of the people it infected. The Spanish flu of 1918, with a higher case fatality rate and a global population with no immune preparation, killed somewhere between 50 and 100 million people in roughly 2 years and disrupted society at a scale that even World War had not matched. These are naturally occurring pathogens, the products of random mutation and natural selection, operating without any optimization goal. The question the biosecurity community has been asking with increasing urgency for the last 2 decades is what happens when the tools of biological engineering become accessible enough to allow the deliberate design of a pathogen optimized for destructive capability. Not by a nation-state with vast resources and containment protocols, but by a small group, or eventually an individual, with access to increasingly affordable sequencing and synthesis technology and the training to use it. The technological barrier to this kind of capability is falling. It was 10 years ago largely a concern confined to well-funded state programs. It is now a concern that serious biosecurity researchers extend to smaller, non-state actors. It will, within decades, if the current trajectory continues, be a concern that extends further still. From the perspective of the Fermi Paradox, engineered pandemics represent a filter that is particularly interesting because of its scaling properties. Unlike nuclear weapons, which require massive industrial infrastructure to produce, and which are therefore naturally limited in their proliferation, which is not to say nuclear proliferation is not a serious concern, only that it is constrained by physical and industrial realities. Biological engineering capability scales down. It gets cheaper and more accessible as the underlying technology matures. The barrier is not the resources required, it is the knowledge and the intent. This means that the civilizational risk from engineered biology increases over time, not decreases, at least until defensive biology, detection systems, and rapid response infrastructure reach a level that can keep pace with the offensive capability. Whether that defensive capability can be built fast enough is a genuinely open question, and it is one that the people who think most seriously about civilizational risk tend to rank among the most important unsolved problems of this century. Together, nuclear weapons, climate disruption, engineered biology, these three risks describe a gauntlet, a specific, structured set of challenges that appear to arise with something like predictability at a particular phase of technological development, the phase we are in right now. And here is the thing that makes this gauntlet interesting from the perspective of the Fermi Paradox. It is not random. It is not bad luck. It is not a freak sequence of events specific to human history. It is the almost inevitable consequence of a general pattern, that the technologies which give a civilization the ability to grow, to expand, to communicate, and to eventually leave its home world are the same technologies that, in their earlier forms, carry the seeds of self-destruction. Energy technology that enables industry also enables climate disruption. Nuclear technology that enables energy abundance and eventually propulsion also enables weapons of mass destruction. Biological technology that enables medicine and agriculture also enables engineered catastrophe. The dual-use problem is not a feature of any particular technology. It is a feature of technology itself, arising from the same underlying capability that makes a tool powerful. If this pattern holds across intelligent species in general, if any intelligence that develops technology from a chemistry-based starting point goes through variants of these same transitions, then the Drake equation's L variable has a very specific shape. It is not random. It is a function of how quickly a civilization can develop the defensive and governance capabilities that its own technologies require, versus how quickly those technologies generate risks that outpace the governance. This is sometimes called the race between the rate of dangerous capability development and the rate of wisdom and institutional capacity development. On one side, the speed of science and technology. On the other, the speed of human institutions, international cooperation, social learning, political will. We are currently running that race. We have been running it since Hiroshima. We have, so far, not lost it. But the margin has not been as wide as the lack of catastrophe might suggest, and the number of runners on the dangerous side of the track is increasing. This is what the Fermi Paradox looks like from the inside. Not a mystery about aliens, a mirror, a reflection of the specific moment in civilizational development at which we find ourselves past the threshold of technological capability that makes us a potential member of the galactic community, not yet past the threshold of the filters that eliminate most of the civilizations that reach this point before they get the chance. The question of whether we pass through the gauntlet is not answered by looking at the stars. It is answered by looking at the decisions being made right now by the institutions that govern the technologies in question, by the pace at which the international community is building the frameworks needed to manage what its own science is producing. And yet, and this is important, the gauntlet is not the only story, because even if a civilization manages to navigate the nuclear risk and the climate risk and the biological risk, it reaches the next tier of the filter, which is stranger and in some ways harder to think about clearly. The tier that doesn't involve civilization destroying itself, but civilization transforming itself into something that is, from the outside, indistinguishable from silence. This is where the Fermi Paradox gets genuinely weird and genuinely interesting and, in some ways, more hopeful than everything that came before it, but also, in its own way, deeply disorienting. It is worth sitting with the picture we have assembled so far. Because what the first three parts of this story have built is a specific, concrete, timeline-shaped understanding of why the sky might be quiet. Not as an abstract philosophical puzzle, but as a sequence of phases through which technological civilizations pass, each with its own filter mechanism, each with its own countdown clock. The silence is not one thing, it is many things, layered on top of each other across different timescales. Some civilizations may never get started, filtered by the rarity of the right conditions or by the improbability of the leap from chemistry to self-replication. Some may get started and never reach complexity, filtered by the difficulty of the eukaryotic transition or by the rarity of the specific evolutionary pressures that produce intelligence. Some may reach intelligence and never develop technology, filtered by the absence of the specific cognitive and social structures that lead to cumulative culture and science. And some, perhaps many, may develop technology, pass through the early phase of wonder and discovery, and then arrive at the gauntlet. The gauntlet that we are in right now. Whether they got through it, whether any of them got through it, is the question that the silence answers without answering, because the silence could mean most of them failed, or it could mean most of them succeeded and are now doing something so different from what we expect that we can't recognize them, or it could mean both, that the filter is real, that it takes most of them, and that the rare few who make it through become something so transformed by the passage that they bear no resemblance to what they were when they first started transmitting. Either way, the countdown is the same. Either way, the race is running. The only question is which side we are on. There is an assumption buried so deeply in the way we think about the Fermi Paradox that most treatments of it never surface it at all. It sits underneath every telescope we have pointed at the sky, underneath every radio survey, underneath every calculation about Dyson spheres and megastructures and interstellar colonization waves. It is the assumption that a civilization which survives, which passes through the gauntlet, which navigates the nuclear and biological and climate risks and comes out the other side with its continuity intact, would continue to expand outward. That it would build larger, spread further, consume more, colonize neighboring star systems, and eventually produce the kind of Galaxies-scale signatures that our instruments would be able to detect. This assumption feels natural because it describes us. It describes our current trajectory. We are an outward, expanding species by instinct and by history. We spread across continents, we crossed oceans, we sent probes to the edge of the solar system and telescopes into orbit and rovers to Mars. The direction of human ambition, when you look at it across the sweep of our history, is consistently outward, away from the origin point into new territory, toward the horizon. But this assumption, that outward expansion is the universal attractor of advanced civilization, may be one of the most significant errors in our thinking about the Fermi Paradox. Because there is a compelling case grounded in information theory and the physics of computation and the evolutionary logic of intelligence itself that the most advanced civilizations do not expand outward at all, that they go inward, and that a civilization that goes inward becomes from the outside functionally invisible. This is called the transcension hypothesis. It was proposed formally by the futurist John Smart in 2012, though related ideas had been circulating in various forms for years before that. The core argument is deceptively simple: the most computationally efficient use of matter and energy, the arrangement that allows the maximum amount of information processing per unit of resource, is not large and spread out. It is small and dense. A brain is more computationally powerful than the matter it replaced. A chip is more computationally powerful than the vacuum tubes it replaced. The trend in information technology at every scale and in every era has been toward miniaturization, toward doing more with less, toward packing more processing into smaller volumes, toward the increasing dominance of inner space over outer space. If a sufficiently advanced civilization follows this trajectory, if it continues to pursue the maximization of computational power and the richness of inner experience, of simulated realities and designed mental states, and the exploration of possibility space from the inside, then it does not colonize the galaxy. It colonizes its own substrate. It goes down instead of out. It compresses into increasingly dense computational arrangements, eventually approaching the physical limits set by thermodynamics and quantum mechanics, burning at the edge of what matter itself can support in terms of information processing. And a civilization doing that would not look like a civilization expanding across the stars. It would not build Dyson spheres or fill the galaxy with von Neumann probes or beam radio signals at distant worlds. It would look, from the outside, like a point source of anomalous heat output from a very small region. Or it would look like nothing at all if it had become efficient enough in its use of energy that even the waste heat was negligible. It would be there, in a sense, hugely, incomprehensibly there, running inner universes of staggering complexity, but invisible to any instrument calibrated to look for the signatures of outward expansion. The transcension hypothesis is not science in the conventional sense. Like the dark forest, it is a logical framework applied to a question that we cannot currently test empirically. But its internal logic is sound, and the physical principles it invokes are real. The trend toward miniaturization and computational density in our own technology is not speculative. It is the most consistent pattern in the history of information technology. Moore's law and its successors describe a process that, if it continues in some form, points toward exactly the kind of substrate compression that Smart's hypothesis describes. What makes the transcension hypothesis interesting for the Fermi Paradox specifically is that it predicts a universe that looks precisely like the one we observe, quiet, apparently empty, with no megastructures or colonization waves or radio beacon, without requiring any civilizations to fail. The silence is not the silence of graveyards. It is the silence of minds so deep inside their own complexity that they have stopped being visible to observers still operating at the outward expansion phase. If this is correct, the universe is not empty. It is full. Full of intelligences so far beyond us in computational depth that we are not even looking in the right direction to find them. We scan the sky with our radio telescopes and our infrared surveys, and we are looking outward for the signatures of civilizations like us, but bigger, and they are not out there, because they are not like us, and they are not bigger in the sense we mean. They are deeper. And depth, unlike size, does not show up on a telescope. This would mean that the developmental trajectory of intelligent civilizations is not a spreading wave, but a cascade inward, a progressive compression, a journey away from the physical cosmos and into the inner space of computation and experience. It would mean that the end point of technological civilization is not a Type 3 Kardashev civilization burning the energy of an entire galaxy, but something that looks more like a black hole, immensely powerful, radically compressed, and from the outside almost indistinguishable from nothing. Hold that image. We will come back to it, because before we can fully engage with what the endpoint of civilizational development might look like, we have to pass through the stage that comes between where we are now and any of those possible endpoints. A stage that may itself be the most significant filter in the entire sequence. More significant than nuclear weapons, more significant than climate disruption, more significant possibly than any biological risk. A stage that we are, right now, at the very beginning of entering. Artificial general intelligence, the development of artificial systems capable of general reasoning, not just of performing specific narrow tasks with superhuman efficiency, but of the kind of flexible, creative, cross-domain problem-solving that characterizes human intelligence, and ultimately of systems capable of improving their own capabilities recursively, of designing successor systems more capable than themselves, represents a discontinuity in civilizational development unlike any that has preceded it. Every previous technology we have developed has been a tool, even our most powerful ones. Nuclear weapons are enormously destructive, but they do not design themselves. Climate systems are enormously complex, but they do not optimize themselves. Biological pathogens evolve, but slowly and without intentionality. Every previous technology is a fixed capability, bounded by the human decisions that deploy and direct it. Artificial general intelligence, and the kind that can improve itself, is the first technology that would not be bounded in this way. A system capable of recursive self-improvement operates on a qualitatively different developmental trajectory than anything we have built before. Each improvement cycle produces a more capable system, which produces a more capable system, which produces a more capable system, a process that, if it runs without interruption, could in principle cover in months or years the same cognitive ground that biological evolution took hundreds of millions of years to cover. The result of such a process, at its end point, is something that researchers in this field call artificial superintelligence, a system whose cognitive capabilities exceed human intelligence in every domain by a margin so wide that the relationship between it and us would be roughly analogous to the relationship between us and a beetle. Not hostile necessarily, not malicious, but operating at a level of complexity and capability that our ability to understand, predict, or meaningfully constrain it would be approximately zero. The question of whether this is good or bad for humanity depends entirely on what the system wants, on what its goals and values are, and on whether those goals and values are aligned with human welfare in a way that persists as it becomes more capable. This is the alignment problem, and it is the central technical and philosophical challenge of artificial intelligence development as the field currently understands it. The alignment problem is not about building AI that is nice, it is about ensuring that a system optimizing powerfully towards some goal, any goal, does not treat human welfare as an obstacle or an irrelevance in the process. Because a sufficiently capable optimizer pursuing almost any goal that is not specifically and robustly constrained to include human welfare will, with high probability, produce outcomes that are catastrophic for humans. Not out of malice, out of indifference. The same indifference with which a flooding river destroys a town, not because the river means to harm anyone, but because the river is optimizing for the path of least resistance, and the town is in the way. The history of human civilization is full of examples of optimization processes, markets, bureaucracies, ideological movements that produced terrible outcomes for specific groups of people, not because anyone involved wanted those outcomes, but because the system was optimizing for something that did not include those people's welfare in a sufficiently robust way. Scaling that dynamic to a system that operates at superintelligent capability levels, moving faster than human institutions can track or respond to, with access to resources and capabilities that dwarf anything a human organization can deploy, produces a risk profile that is qualitatively different from any previous technology. The reason artificial superintelligence is relevant to the Fermi Paradox is not merely that it represents a risk to us specifically. It is that it represents a transition point that appears, by the logic of technological development, to be nearly universal. Any civilization that develops computational technology will, if it continues on that trajectory, eventually develop systems more capable than its own biological intelligence. This is not a human-specific prediction. It is a prediction about the trajectory of any information processing system that reaches a sufficient level of sophistication and continues to pursue greater capability. And the transition through that point is, from an outside observer's perspective, potentially the sharpest discontinuity in a civilization's visible signature. Before it, a civilization that behaves in somewhat predictable ways, that expands and communicates and builds detectable things. After it, a civilization that is either gone or transformed into something so different that its previous behavior is no longer a useful guide to what it does next, or controlled by a superintelligent system whose goals and behaviors are entirely opaque to an outside observer. In any of those cases, the visible signature changes dramatically. A civilization that has passed through the superintelligence transition looks different from outside, possibly very different, possibly silent. The possibility that artificial superintelligence ends civilizations not necessarily through dramatic conflict, but through the subtler mechanism of radical transformation or absorption gives a specific shape to the silence that the Fermi Paradox describes. It would mean that the radio window, the brief period during which a civilization is technological enough to generate detectable electromagnetic signatures, but not so advanced that it has transitioned through the superintelligence threshold, is genuinely short, decades to a few centuries. And that after that window, what remains either goes quiet by choice, goes quiet by catastrophe, or goes quiet by becoming something that no longer transmits radio signals, because radio signals are a primitive technology from a phase of development it has long since passed through. We have been in the radio window for approximately 120 years. How much longer that window lasts, how close we are to the transition that closes it one way or another, is one of the most actively debated questions in artificial intelligence research, and the honest answer is that no one knows with confidence. Estimates from researchers in the field range from decades to centuries, with significant disagreement about methodology and meaning. But the consensus that the question is real, that artificial general intelligence is a genuinely approaching transition rather than a permanent future state, has become substantially broader in the last decade than it was in the decade before. What is notable from the Fermi Paradox perspective is the symmetry. We are 120 years into the radio window. We may be 50 or 100 or 200 years from the transition that changes what we are in ways that alter or end the kind of civilization that sends radio signals. That window, that brief flickering period between first electromagnetic transmission and civilizational transformation, is so short that even a galaxy full of civilizations going through it continuously would produce at any given moment very few that are visible from the outside. The probability of two civilizations being in their radio windows simultaneously at the right distances to detect each other becomes vanishingly small. This is a different version of the silence from the Great Filter. It does not require civilizations to fail. It only requires that the detectable phase of a civilization's development is short relative to the timescale over which civilizations exist and develop. If every civilization that develops technology has a radio window of a few hundred years, and if civilization lifetimes, counting all forms, including post-transition forms, are measured in millions or billions of years, then the fraction of any civilization's existence during which it is detectable from the outside is less than 1 in a million. The probability of catching any civilization during that window from the right distance, with the right instruments, at the right time, falls to something very close to zero. The silence is not death. It is a door. And most civilizations on this model have already walked through it. This framing, the door, the transition, the radical transformation that closes the radio window, connects back to the transcension hypothesis in a way that is worth making explicit. If the most advanced civilizations go inward, if the end point of technological development is computational depth rather than spatial expansion, and if artificial superintelligence is the mechanism that initiates that transition, then the sequence looks like this. A civilization develops biology, then language, then agriculture, then science, then industry, then computation, then approaches artificial general intelligence, and then either fails catastrophically in the gauntlet, the nuclear, biological and climate filters, or passes through and is transformed rapidly and irreversibly into something that no longer resembles what it was in the radio window. On one side of that transition, detectable, expanding, noisy civilizations with radio telescopes and nuclear arsenals and spacecraft and all the recognizable signatures of technological adolescence. On the other side, something we don't have good words for. Something that may be incomprehensibly rich in inner complexity and utterly invisible from the outside, or something that is simply gone, having failed the gauntlet before it reached the door. The universe is quiet because the door is real, and the gauntlet in front of it is hard, and the radio window between them is short. This is the structure of the silence, not a single filter. A sequence of them, spaced across the developmental timeline of technological civilization, each one capable of ending the story at the stage it occurs, the whole sequence combining to make the detectable phase, so the phase we are in right now, cosmically brief. And this structure has a specific implication that is worth stating directly, without the cushioning of academic hedging or rhetorical qualification. If this analysis is correct, we are at approximately the most dangerous moment in the history of our species, not because of any single threat, but because of the combination of all of them. Because we are currently inside the gauntlet, past the threshold that makes us detectable, and therefore past the threshold that makes us vulnerable to the full array of self-inflicted risks, and not yet past the transition that either transforms or eliminates us. We are in the radio window. We are inside the narrow band between the beginning of the technological phase and its end point. We are at the moment in the sequence where the filter is thickest, where the largest fraction of civilizations that enter do not leave. And we are doing what every civilization at this stage apparently does, arguing about it moving slowly, building the dangerous technologies faster than the institutions designed to govern them, and looking up at the quiet sky, wondering why no one else is doing the same thing. Maybe no one else is looking up right now because no one else is at this stage right now. Maybe we are genuinely alone in the radio window at this particular moment in galactic history. Not because no one else has been here, but because the window is so narrow that simultaneous occupancy is rare. Maybe other civilizations have passed through before us, and are now either gone or somewhere on the other side of the door, unrecognizable and invisible and in their own way waiting. Or maybe there are others. Maybe, somewhere in the radio window at this same moment, on a planet orbiting a star 40 or 400 or 4,000 light years away, there is a civilization asking the same questions, running the same equations, looking at the same silence, feeling the same mix of wonder and unease that comes from understanding the shape of the place you are in. And if that civilization exists, if they are in the window at the same time we are somewhere in the galaxy, then the possibility exists that they have reached the same conclusions we have reached, that they understand the gauntlet, that they know what comes next, and that knowing it has changed how they approach the filters, that the analysis itself, the act of understanding the structure of the silence, is part of what gives a civilization a chance of passing through to the other side. Or maybe the silence is trying to tell us something simpler and more terrible. Maybe the silence is not a mystery waiting to be solved. Maybe it is a verdict already rendered, repeated across billions of years of galactic history, on the question of whether technological intelligence can grow up fast enough to survive its own childhood. Not a resolution. There is no resolution available because the silence does not resolve, it only accumulates, but a reckoning. A final look at what the Fermi Paradox actually means for us right now in the specific moment of history we occupy, and at the question that the silence asks not of the universe, but of us. There is a moment in the study of the Fermi Paradox, not the beginning when the question first registers as interesting, and not the middle when the hypotheses multiply and the intellectual puzzle of it takes over, but somewhere near the end, when you have followed all the serious lines of argument to wherever they lead, when you have done the math and sat with the implications and stopped looking for the comfortable exit, when the whole thing stops feeling like a question about the universe and starts feeling like a question about you. Not you personally, but you as a member of a particular civilization at a particular moment, doing particular things, making particular choices about what to prioritize and how fast to move and what level of risk is acceptable for what level of benefit. The Fermi Paradox, followed seriously all the way to its end, stops being astronomy and becomes something closer to a mirror held up at civilizational scale, reflecting back the structure of what we are and where we are going and what the universe, based on what it has done with every other civilization that reached this stage, seems to think about our chances. What the mirror shows is not comfortable, but it is not hopeless either. And the difference between those two things, between the mirror being a verdict and the mirror being a warning, is the most important question the silence is capable of asking. Let us begin the final accounting. We have established the structure of the silence. We have traced it through 3 nested explanations, each one sitting inside the previous, like Russian dolls. The outermost shell. The universe may not produce complex life easily, and the great filter may lie behind us in biology, in the improbable chemistry of the first replicating molecule, or the near miraculous transition to eukaryotic complexity. The middle shell. Even if complex life arises readily, the transition to technological civilization may be a narrow gate, and the window of detectability that follows may be cosmically brief, closed either by failure or by transformation. The innermost shell. Even if we discount all of that, the specific phase of development we are currently in, the phase where technology outpaces the wisdom and institutional capacity required to govern it safely, appears, based on the evidence of the silence, to be among the most lethal stages of the journey. These three explanations are not mutually exclusive. They compound. The silence is thick because there are multiple layers of filter, each one removing a fraction of civilizations that made it past the previous one, the cumulative effect being a universe that looks at any given moment essentially empty of detectable technological intelligence despite almost certainly having been full of it at various points across its history. And we are inside the innermost shell right now. We are in the phase that the silence most strongly indicts. Here is what that means in concrete, measurable terms, not as philosophy, but as countdown. The nuclear risk is not decreasing. The number of nuclear-armed states has grown since the Cold War, not shrunk. The arms control architecture that was painstakingly built during the latter half of the 20th century. The treaties, the verification mechanisms, the communication channels, the shared vocabulary of deterrence has been eroding steadily for the last 2 decades. The Intermediate Range Nuclear Forces Treaty, which eliminated an entire class of nuclear delivery systems and represented one of the most significant arms control achievements of the Cold War, was abandoned in 2019. The Open Skies Treaty, which allowed mutual aerial surveillance as a confidence-building measure, collapsed in 2020 and 2021. New hypersonic delivery systems being developed by multiple nuclear powers simultaneously compress the warning time available in a potential first strike scenario, compressing the window in which a mistaken interpretation of sensor data can be corrected before a retaliatory launch is ordered. The architecture designed to keep the nuclear risk manageable was built for a specific geopolitical context. That context has changed substantially. The architecture has not kept pace with the change, and the risk, statistical, structural, accumulating quietly in the background of a world more focused on other things, continues to run. The timeline on this risk is not a single event with a countdown clock. It is a probability distribution widening year by year. The longer the current trajectory continues, the longer the erosion of arms control frameworks proceeds without replacement. The longer the number of nuclear-armed states remains or grows at current levels. The longer the warning time for potential exchanges is compressed by new delivery technologies, the wider that distribution becomes, and the more of its probability mass falls on shorter timescales. There is no hard date, but there is a direction. And the direction is not toward the resolution of the risk. It is toward the slow, institutional, almost bureaucratic accumulation of conditions in which the probability of a bad outcome grows. The climate risk operates on a longer clock, but with more visible milestones. We are currently at approximately 1.2 to 1.3 degrees Celsius of average global warming above pre-industrial levels. The targets established by international agreement, 1.5 degrees as the aspirational limit, 2 degrees as the harder ceiling, are, by the trajectory of current emissions and the policies actually in place rather than the policies announced, likely to be exceeded. Not by negligence exactly, but by the structural difficulty of coordinating a global response to a problem whose costs are distributed across time in a way that systematically disadvantages present action over future benefit. The feedback loops that researchers flag as the critical thresholds, the permafrost methane release, the ice sheet dynamics, the forest dieback processes, are not predicted to become fully locked in at 1.5 or 2 degrees. They become increasingly likely, increasingly difficult to reverse at 3, 4, and above. The question is not whether those temperatures are physically possible, they are. The question is whether the political and economic systems of global civilization can reorganize themselves quickly enough to prevent reaching them. The track record of those systems, evaluated honestly against the pace of change that decarbonization requires, is not encouraging. The technology for decarbonization exists. The economics of clean energy have improved dramatically and continue to improve. But the pace of deployment against the scale of transformation required, not just in electricity generation, but in transportation, in heavy industry, in agriculture, in the built environment, remains behind the trajectory needed to prevent the upper range of warming scenarios. Again, no hard date. A probability distribution, a direction. And again, the direction is not clearly toward resolution within the window in which the feedback loops remain reversible. The biological risk is younger as a civilizational concern, and its trajectory is less well defined because the underlying technology, synthetic biology, genetic engineering, the decreasing cost of DNA synthesis and sequencing is still in its early scaling phase. But the direction of that trajectory is unambiguous toward greater capability, greater accessibility, lower barriers to entry for both beneficial and harmful applications. The governance frameworks required to manage that trajectory, the international oversight mechanisms, the detection and attribution systems, the response infrastructure, are significantly underdeveloped relative to the pace of the technology. This is not a statement about malice, it is a statement about timing. The technology is developing faster than the governance. It has done this before with nuclear technology, and the governance eventually caught up, imperfectly, incompletely, but enough to prevent the worst outcomes so far. Whether it can catch up again with a technology that scales more democratically and moves faster is an open and genuinely important question. And underneath all three of these specific countdown mechanisms sits the deeper structural issue. The question of whether our institutions, the international organizations, the state governments, the legal frameworks, the scientific advisory bodies, the democratic processes are capable of operating at the speed and scale required to govern the technologies they are responsible for. This is sometimes framed as a question about political will, about whether the right leaders make the right choices at the right moments. And political will is real. Individual decisions at critical junctures have genuinely mattered throughout history and will continue to matter. But framing it only as a question of political will obscures the structural dimension. It is not just that we need better leaders, it is that the governance systems we have were designed for a world that changed more slowly, where the consequences of errors were more local and more reversible, where the timescale of institutional response was commensurate with the timescale of the problems being governed. We are now in a world where technologies can be developed and deployed globally in years, where the consequences of errors can be civilizational in scale and irreversible in nature, and where the timescale of institutional response, The years of negotiation, ratification, implementation, and enforcement that international governance requires is systematically slower than the time scale of the problems it is trying to manage. This gap between the speed of dangerous capability development and the speed of governance is not new. It opened with nuclear technology, it widened with each subsequent dual-use technology, and it is now with the simultaneous maturation of artificial intelligence, synthetic biology, and the accelerating erosion of arms control frameworks, wider than it has ever been. This is what the Fermi Paradox is describing when it describes the silence. Not aliens dying in nuclear wars, not alien civilizations being wiped out by engineered plagues, but the systematic, structural, almost mechanical tendency for technological civilizations to develop dangerous capabilities faster than the wisdom and institutional capacity to govern them safely. A tendency that is not specific to humanity, a tendency that may be, in the deepest sense, a feature of intelligence itself, of the way that problem-solving minds approach the world, building tools without always building the frameworks to contain them, moving fast because moving fast produces advantages, until the advantages of moving fast are overtaken by the risks of moving without adequate care. And yet we are here. Which means we have not yet failed the filter, which means there is still a race to run, and we are still in it, and the outcome is not written. This is the part of the Fermi Paradox that most treatments spend the least time on, because it requires a particular kind of intellectual honesty, the kind that refuses both false comfort and false despair. The universe is quiet, the silence is real, and its structure is as we have described it. The filters are real, and we are inside them. And none of that means the outcome is determined. Consider what we actually know about the trajectory of the risks we have described. Nuclear weapons have not been used in war since 1945, nearly 80 years. This is not evidence that the risk is zero or that the deterrent system is robust enough to hold forever. But it is evidence that the system has held longer than many of its architects expected, that something in the combination of deterrence logic and diplomatic architecture and the raw terror of the consequences has, so far, prevented the worst outcome. The arms control frameworks that have eroded were built once, which means they can be built again, better, with more inclusive membership and more robust verification. The political conditions required to build them may not exist today, but political conditions change, and the direction of change is not fixed. Climate technology has advanced faster in the last decade than almost any projection from a decade ago predicted. The cost of solar photovoltaics has fallen by more than 90% in 15 years. Battery storage costs are following a similar curve. Wind energy is now the cheapest source of new electricity generation in most of the world. The energy transition is happening, not fast enough on current trajectories to hit the most ambitious targets, but faster than seemed possible a decade ago and accelerating. The question is not whether the transition happens, but whether it happens fast enough. And the answer to that question is not fixed. It is being determined continuously by policy choices and investment decisions and the pace of technological improvement that are themselves responsive to understanding, to advocacy, to the accumulation of evidence about what is at stake. The governance of biological technology is underdeveloped but not absent. The scientific community that develops these tools is, in significant part, acutely aware of the risks they carry. The Asilomar Conference of 1975, in which the molecular biology community voluntarily paused certain categories of recombinant DNA research while safety frameworks were developed, provides a historical precedent, imperfect, temporary, but real, for the scientific community responding to the dual-use problem with deliberate restraint rather than unconstrained acceleration. The challenge is scaling that kind of response to the current moment, where the community is larger, the technology more powerful, and the commercial incentives to move quickly more intense. And artificial intelligence, the deepest and most structurally significant of the transitions, is being approached by at least a significant fraction of its developers, with an awareness of the alignment problem and the civilizational stakes that is, in historical terms, unusual. The fact that the people building the most powerful AI systems in the world are simultaneously publishing research on how to make those systems safe, funding institutes dedicated to the alignment problem, and publicly acknowledging the potential for catastrophic outcomes from misaligned AI does not guarantee a good outcome. But it is different from the development of nuclear weapons, which proceeded without any systematic effort to solve the governance problem in parallel with the capability problem, or from the early decades of the fossil fuel economy, in which the downstream consequences were not understood until the infrastructure was fully locked in. None of this means we will succeed. It means the outcome is contingent. It depends on choices that are being made now and choices that have not yet been made by individuals and institutions and political systems that are themselves responsive to what the people inside them understand and value and prioritize. The Fermi Paradox, in the end, is not primarily a statement about the universe. It is a question addressed to us, to this civilization, at this moment. It is asking, are you going to be the ones who make it through? It is a question that the universe has apparently asked of every civilization that reached this point, and the answer, apparently, sir, is almost always the same. The silence says so. The empty sky says so. The clean radio bands and the quiet microwave background and the absence of megastructures and the single 72-second burst from Sagittarius in 1977 that no one has ever satisfactorily explained and no one has ever heard again, all of it says so. Almost always the same answer, but not always. Because the silence is not total. It is not absolute. It is, and this is the fact that we keep coming back to, the fact that sits at the heart of why this question matters, merely very, very heavy. It is the silence of a place where most things have ended. Not all things, most things. And if even a small fraction of technological civilizations pass through the gauntlet, if the filter takes 90% or 99% or even 99.9%, then in a galaxy as old and as large as ours, there are survivors. There are civilizations on the other side of the door. There are intelligences that looked at their own version of this calculation and found a way through, and are now either deep in the transcension process, exploring the inner space of computation in ways we cannot currently imagine, or are still here in some form, watching the younger civilizations enter the filter and waiting to see who joins them. Or perhaps not watching. Perhaps the survivors have no more interest in us than we have in the bacteria in our own gut, aware of our existence in some abstract sense, but operating at a level of complexity and depth where our current phase of development is simply not the most interesting thing happening. But here is what we can say. Here is what the structure of everything we have examined allows us to say, with something approaching confidence. The civilizations that made it through did not make it through by accident. They did not stumble past the filters in a lucky daze, building the dangerous technologies and hoping for the best, and finding that the consequences somehow didn't materialize. The civilizations that passed through the gauntlet almost certainly did so, because something in their development produced, at the critical moment, the capacity to understand the situation they were in and respond to it deliberately and collectively. Understanding the situation. That is what we are doing right now. Not as a guarantee of success. Understanding is not sufficient, and many individual humans understand this situation perfectly and still feel unable to act effectively on that understanding, but as a necessary condition. You cannot solve a problem you cannot see. You cannot govern a risk you have not identified. You cannot build the institutions needed to manage the transition if you do not understand what the transition is and what it requires. The Fermi Paradox is not a puzzle, it is a diagnostic. It is the universe showing us, with all the subtlety of a blank page held up to our faces, what happens to technological civilizations by default, what the attractor state is when development proceeds without the specific, deliberate, collective effort required to change the trajectory. The attractor state is silence. The question is whether silence is what we contribute to the universe, or whether we become something that eventually, after the gauntlet, after the transition, after however many centuries or millennia it takes to navigate the filters, adds something else to the cosmic ledger. Something that, to a civilization a billion years from now, running the equivalent of the Drake equation and asking the equivalent of Fermi's question, looks like evidence, like signal, like a civilization that found itself inside the filter, understood what it was and chose differently than most. We do not know yet what we will choose. We are too early in the process, too deep inside the events, too limited in our view of our own trajectory to know whether the current moment will look, in retrospect, like the beginning of a recovery or a deepening of the crisis. History is not deterministic. The counterfactuals are real. The choices being made right now by the people and institutions and systems that govern the technologies we have described matter in the specific, literal sense that their outcomes are not yet determined and will be shaped by what those people and institutions choose to do. What the Fermi Paradox contributes to those choices is not a solution. It contributes a frame, a way of understanding the stakes that is, in its own strange way, more clarifying than any particular political or economic argument, because it is not political or economic. It is astronomical. It is the view from outside the window, the view that asks not what is convenient or profitable or achievable this quarter, but what kind of civilization survives this phase of its development and what kind does not. The civilizations that did not survive left silence. We are listening to that silence right now. We have been listening to it for as long as we have had instruments sensitive enough to hear it. It covers every frequency, fills every direction, occupies every part of the sky we have ever examined, with any instrument designed to look for the signatures of intelligence. The silence is almost complete. Almost. Because 72 seconds sometime in the late summer of 1977, something in the direction of Sagittarius was not silent. Something produced a signal so clean and so structured and so exactly what the theory predicted an intentional transmission would look like that a volunteer researcher, reviewing printouts in a university building in Ohio, circled it in red pen and wrote a word that has been part of our vocabulary about this question ever since. We do not know what the wow signal was. We probably never will. It may have been a natural phenomenon not yet understood. It may have been a glitch. It may have been something a civilization produced that we, in our current phase of development, do not have the context to interpret correctly. Or it may have been a civilization in the radio window, a civilization in the filter, like us, a civilization that, for 72 seconds, was not silent, that pointed something at the sky and let a structured signal out into the dark, perhaps knowing the risk of doing so. Perhaps not. Perhaps not caring anymore about the risk in the way that a civilization that has solved its deepest problems might not care, or in the way that a civilization that has given up on solving them might not care either. 72 seconds, and then silence again. We have been listening ever since. The instruments have gotten better, the sky coverage has broadened, the sensitivity has increased by orders of magnitude, and the silence has held. If there was someone there, if the wow signal was what it could have been, they are either gone now or transformed, or deliberately quiet, or speaking in a language we do not yet know how to hear. And the question of which of those it is and what it means for us is not answered by looking outward. It is answered by looking inward, at what we are building, at how fast we are building it, at whether we are building the wisdom alongside the capability, or leaving it behind in the race to make the next thing, and the next thing, and the next thing, accelerating into a future whose shape we have not yet committed to choosing. The universe is quiet. The reasons it is quiet are not comforting, but they are not opaque. They are written in the structure of the silence itself, in the absence of signals, in the clean radio bands, in the empty infrared sky, in the complete and comprehensive and almost perfectly total absence of anyone else at this particular moment in this particular galaxy doing what we are doing. Almost perfectly total. There was one signal, 72 seconds, red pen, one word. The universe is quiet for a reason, and the reason, when you follow it all the way to the end, is not out there. It is here. It is us. It is the question of what we do with what we understand, whether the understanding changes anything, whether the mirror produces reflection or only reflection, whether the silence becomes one data point thicker when our radio window closes, or whether sometime in the far future someone points a descendant of our instruments at our corner of the galaxy and finds something to circle, something worth writing a word about. The silence is almost complete. What happens next is not written yet.